to talk about something a little bit different and unusual at the JVM Language Summit, not the JVM. I'm going to talk a little bit about how .NET deals with the value types and generics in our system. What do we want to talk about here? We want to talk about how does .NET use value types and what are the scenarios on them? How do they work in .NET? What's different about them? Possibly some of the changes we have as compared to, say, Valhalla. And what are the problems that we have in our runtime because we have value types? And after that, we'll start talking about how generics and value types interact. There's a bunch of interesting semantics of how they can come together and how they work. And they come with their own large pile of runtime challenges. Those challenges, they combine with the challenges of value types to produce an even more interesting result. And so I'd like to start with a little bit of terminology. We use a little bit of different terminology in .NET, so I'll get started here. In this talk, I'm primarily talking about value types, but there's a number of other terms that I'd like to use. First, we have the concept of a reference type. That would be a type which is referred to with an object reference. And that would be any class, any array, and if you've boxed a value type, you access that as well through an object reference. In .NET, a value type is defined by its data. It's not an optimization to flatten. It is a requirement. It's always flattened, unlike the Valhalla prototype. We can place it as a local variable. It can exist as an evaluation stack on the logical execution environment, or as in a field of any type, etc. And then that brings to a number of ways to point at the memory of type. In .NET, value types still have identity. You can create pointers to them. If you have a local, it's that local. But there's other forms of pointers in .NET. We'll start with the most familiar to Java. That's the object reference. Works a lot like, it's the same. If you have a class, you have an object reference to it. You allocate an object on the heap, logically, on the GC heap. That's how that works. But when you have a pointer, if you want to access the identity of a given value type, you use a pointer. And we have two different concepts of pointers. We have pointers, which are very much just the C concept of a pointer, useful in unsafe code for access to memory that may or may not be on the GC heap, may or may not be managed by the runtime, et cetera. But we have a subset of that kind of pointer, which we call a managed pointer. And a managed pointer is the only kind of pointer that's allowed to point onto the GC heap. And, well, as long as there's no pinning. These managed pointers may point to the interior objects on the GC heap, and so we, for performance reasons, restrict those pointers to only exist on the stack or in local variables. .NET has the concept also of passing a value by reference to a function, and this is the most visible use of managed pointers in .NET. In C#, these are referred to as ref parameters. Regular pointers, we don't report to the GC in any way, so use of them it's possible to generate unsafe and non-type safe code. And when I'm talking about pointers here, through most of this talk, I'm referring to operations that you can do with either a pointer or a managed pointer, as they're somewhat interchangeable. So what are the design goals? What are the benefits of using value types in .NET? And we use them to specify how an operation is to be performed. We say if it's a value type, it's always flattened. A customer or developer can be confident they know exactly what's going to happen when it's placed into memory. And we use these to simplify development for that sort of situation. You can write a list of a value type or a class, and it all works very simply. We don't find that developers are confused by the way we've expressed all of this. Now, in addition to simple scenarios, if you want to really get into getting great performance, you sit down, you can very carefully use classes, you make your types out of classes and value types, you can control your memory layout very specially with .NET, and you get exactly the behavior in terms of usage that you would expect to get from looking at the C#. You don't say, there's no, the JIT will optimize this, or the VM may choose to. It does. So it's a guarantee that you get, which leads to the next idea is we take a large advantage of static and local analysis. We don't do very many whole program or dynamic analysis over the entire system. We attempt to do most of our analysis over at an immediate moment, when we JIT it. And we don't typically rejit more than once at most. And even then, that rejit operation, it looks at one method to compile it. Maybe it inlines a few things, but it only looks at those things that it pulls in. And this yields what we believe is predictable performance. We really have a goal of being able to predict exactly what the performance characteristic should be. Maybe not the exact number of like how fast you'll be, but if I'm going to make a change, I can understand the order of magnitude of impact it's going to have on the system. And I can be very confident that it will remain to have the same impact, sort of regardless what other things might happen within the process. In .NET, we provide a unified type system. Everything derives from object if it's a user-defined type. And we can use these things as normal type, all the value types derive from object, just like regular classes. You can use them as if they derive from object by casting them to object, but that's boxing. Unlike the Valhalla project, we do have identity, as I said, in value types. So we have an identity of it's on the stack, it's in a field, it's on a local, but also the identity of I've converted it to an object. I can lock on it. It's kind of an odd thing to do, but you can box an object and then lock on it. You can box it twice and then compare them, use a reference equals to compare them for equality, and we'll actually say false, and we're required to maintain that behavior. This gives the developer a choice of exactly how the memory is used. And value types like classes, they can have fields, they can have methods, they can have properties, events, all the things you can do, but the memory layout is just handled a little bit differently. Also, we talked in the last talk, the presenter talked about how value type arrays are covariant with object arrays. We don't do that. But we have gone down some similar paths. For instance, the default value for a value type, it's all zeros. Similar to, we consider the default value for a reference type field, it's null. So we unify those concepts. Oops. Yeah, there we go. So what do we use value types for? We use them to define the primitive types. All primitive types are just regular value types in .NET. Oh, sorry. Okay, I lost track of where I was. Sorry. So what are value types from the point of view of the runtime? All of our primitive types are value types. They derive from system value type, which derives directly from system object. It's a very bifurcated system. You cannot derive from a value type itself. It's a single node in the inheritance hierarchy. You have your value type that derives from system value type that derives from system object. You can access fields from some value type that's been given an identity by working through a pointer. Our value types are mutable to enable scenarios such as returning an iterator that has a different value. You can call next on it, it'll give a different value. But when you assign a value type, you're cloning data, and it's guaranteed that that is exactly what has happened. It's generating a clone which has a separate identity. Yeah, that's where I got lost. So why do we support value types? We use them, as I said, to define value types. We use them to avoid heap allocation. In the previous presentation, there was a example of reducing allocation by 1000x. This does happen in practice. We see customers actually do this. We do this internally in our frameworks where we say, we could optimize this. We'll use a value type here, and we'll get it to go a lot faster. We match data layout with the C ABI on the platform. .NET, we share a memory space with the rest of the C code or Rust or Go or whatnot that is executing in the process. And we support direct access to that memory. And we support that through value types, through pointers to value types. We share the memory layouts with that sort of thing. Which leads to another point of not just avoiding heap allocation, but we can avoid GC heap allocation instead. It's possible to use heap memory that isn't GC heap memory. Call something like malloc or free to work with your memory if you have some reason not to want to get involved with garbage collection time and that sort of thing. And things like high-performance data structures. The concept of an array of structures is very natural in C#. You just write a struct, put some values in it, make an array, you're done. Or a list of T. Well, you just throw your structure in there, and then what you have effectively is an array of structures. And then there's generic specialization, which we'll get to later. So when I talk about defining value types, or defining primitive types, all of the primitive types are just value types. All the SIMD types that the JIT knows about to generate vectorization code, they're just value types. And they're not special through most of the runtime. They're just handled like every other value type, very, very simple. We specialize them in the JIT, in the IL, in a couple places, in the metadata, so we can load types. We ask the question of what is this type, how do we define it in our file format. We have some specialization for primitive types, but not that much. And then you'll find throughout various libraries, sometimes value types will be specialized, or primitive types will be specialized, but typically they don't have to be. And then we can talk about avoiding heap allocation. So you can create a value type and you can put code in it that encapsulates functionality, you can call a function that it'll change what your value type has in its fields, et cetera. But you can do this very naturally, and you don't need to imply the use of the heap, and the runtime is not permitted to use the heap to store the data. Implementing multiple return values without allocation, very simple. We implement a generic type that's specialized. We implement a value tuple, which is a tuple that is a value type. And the Roslyn compiler is able to implement multiple return values very simply. It will be a great addition to Java when they get that feature. And the function object pattern without requiring allocations makes it easier to know exactly how things will work. This is where you get the benefits of that 1000x reduction in allocation. It's wonderful. But this isn't transparent to developers, whether or not something's a reference type or a value type. Because we have identity, it's not transparent. On top of the heap allocation reduction, we can remove GC heap allocation. We don't mandate that value types exist at any location in memory that the VM controls. And so we have general purpose heap allocation APIs in the .NET API surface. You can just allocate memory and return it as a pointer, access that memory via unsafe code. But you can also take that unsafe pointer and convert it to a managed pointer and pass it off to code, which is safe. And so, yes, there's pieces of code that are unsafe and not very trustworthy, but then they can call off to routines that are guaranteed to work correctly via the type safety model of the C# language. And of course, the big reason is why would you want to use value types? Because you can make stuff run faster. Building an array of structures, it's simple and easy to do with .NET. It's a very common data structure. Well, it's typically actually wrapped in a generic type, but we'll cover those later. On top of building an array of structures, .NET has relatively recently added the concept of a span of T. A span of T is a pointer and a bound and a size. So you can do type safe, bounds checked, access to arbitrary memory. This memory pointer can be directed at a GC heap, at a stack allocated array, at some piece of memory that came from the OS I/O stack to do zero copy network I/O. And of course, there's also unsafe pointers, as I've talked about a few times. If you can do it in C and C++, it can typically be done in C#. Typically useful for things like interacting with C APIs for doing high-performance math, things like BLAS or image processing code or possibly TensorFlow. Lots of options in this space. And I'll talk about specialization later, but now I'd like to talk a little bit about boxing value types. What is a boxed value type? It's a value type which has been allocated onto the heap as an individual object. I called them out separately from value types in the earlier slide because unlike value types that exist within other objects, they have object identity. The boxed objects follow typical object-based rules around object identity and lifetime, and they're very much not a transparent feature of .NET. They're very user visible, and you can access them through a small selection of APIs. Most interestingly, you can find out what type of an object, what type an object is using the isInst IL operation. You can take a boxed object and you can unbox that object and put it on the stack to access the fields and such. Given a boxed object, if the value type implements an interface, you can call interfaces on the boxed object as it exists in the heap. And then, any function on a boxed object can be invoked via a delegate or via reflection. So I talked a little bit about calling functions on value types, and instance functions in particular. So the this pointer to a value type instance function, it's a managed pointer. This allows the function to modify the contents of the value type, to adjust the fields on it. This managed pointer may point onto the GC heap. It may point to an object not on the GC heap again, or may point to a local variable. It can point to anything. And that's really one of the powers of the mutability that we get. As Neil's question earlier to talk about this, it's a really interesting distinction. We find it very useful. You can use it to implement things like iterators easily. But it also adds new problems. Because that first parameter is a managed pointer and not an object reference, it may not actually point at the same location in memory. In .NET, objects have a header, and then there's the data that follows them. But a managed pointer to a value type simply points at the data. There's this distinction between object references and managed pointers to the data of a value type. And in the CLR runtime, it's off by one pointer. And so this adds the concept of when you call a function that's on an actual boxed value on the heap, it needs to be unboxed to be executed. But the unbox is simply this pointer is adjusted and then passed on to the next function. This adds a bunch of complexity to our system, which making the VM more complex and the death by 1,000 cuts problem is absolutely a major concern for any developer working in the system. Which brings us to runtime challenges. Most of these runtime challenges are driven by the idea that value types exist because they are a specification of how to do work for us. There's a number of problems here. Because the design philosophy of specification of how an operation is performed, and the very flexible capabilities of value types, it's quite difficult for the runtime to reorganize things based on its whims or heuristics. We have to hide every possible difference such that it appears that exactly what they wrote in IL is what happens. As an example, in IL, capturing the address of a value type it's a common thing. And then you can pass that address to another function via a ref parameter. Well, what does this do to escape analysis? It means that your local variables aren't necessarily local. They can be passed out and then modified by other code. Possibly that managed pointer was converted to an unsafe pointer and passed to C code. It's actually perfectly legal in .NET. This also adds other weird problems, such as value type layout is visible to developers through these pointers. And then we have extra complexity just from having different types of type. We have these I called out unboxing stubs, but there's a lot of other special cases throughout the runtime. I did a quick count last week for is value type in our VM directory, just the not the code generator, but just the type system environment and that sort of thing. So 240 different special cases for handling value types. It adds up pretty rapidly. The existence of value types has driven us into having the concept of passing a value by reference. It's very useful, but it's also very dependent on what exactly your value type is. Some value types, it's not worth passing by reference. An integer passed by value is a much more efficient technique. Maybe you would only use pass by reference for semantic goals, but if you have 800 element structure that's a couple kilobytes in size, you probably don't want to pass that by value all that often. You would want to pass it by reference. And so now customers will find themselves trying to pick between, do I want the semantic benefits of pass by value or pass by reference, or am I using it for the performance benefits? What does the runtime do in those cases? How do we handle that? And generally, the support for value types adds a lot of complexity to all of the ABI parts of our system, all of the architecture-specific parts of our logic. Every processor has a different ABI. Every operating system typically has a different ABI on top of that. Because of our support for interop, we support at least 4 different ABIs on each platform. This leads to 20, 30 different ABIs we support within the code generator. It's a giant mess. And value types are the part of the ABI that is complicated. On top, yes? Oh, yeah. So I've talked a lot about value types and how they impact our system. But now I'd like to talk a little bit about generics. To begin, in .NET, generics are a runtime concept as well as a language concept. We call these reified generics, and they're always reified. And this has lots of consequences for the runtime and for the semantics of languages that build on this runtime. The general core rule that it's possible to use a generic type variable in any part of a type for any reason that any other type might be used for. And let's trace one series of behaviors that follows from this concept. Any field, including a static field, can be of type T. From that, it follows the memory layout of static variables is dependent on the type variable. Thus, .NET requires that there's a separate copy of statics for each instantiation of a generic. Because we have separate copies of statics and functions for each instantiation, we also have separate reflection type objects for each instantiation of a type to allow reflection to access the static variables on types that differ only by instantiation. This leads to the requirement that generics are always instantiated when they're used. Expressing generic types within the runtime provides a number of benefits, such as type safety with casts, and this ability to produce better errors, constraints in generics, and the runtime, which the runtime can and does verify before you can load the type at all. But there's lots of these extra capabilities that come along with generics and value type and generics that come with reification. So what about generics and value types? Any generic can be instantiated over a reference type or over a value type. Field or a local of a type variable holds either the data of a value type or an object reference to a reference type. In order to make this work, in .NET we had to implement a reified generic model, or I suppose figure out the sort of things that Java is dealing with now in Project Valhalla. Reified generics allow our generic classes to transparently work with reference types and value types because we've defined an IL that is compatible between the two, even in the presence of pointers and object references and whatnot. This enables our collection classes to work efficiently on all sorts of types. Our collection APIs can be used just as easily as with ints as with objects. But the interaction isn't limited to just enabling a generic type variable to be used in the public API. A generic type may be instantiated with another generic type. For instance, a dictionary of t, u uses a key value pair of t, u to hold its hash table. In general, in the .NET runtime, we say that both generics and value types are powerful features, but the real complexity and power of the two come when the features are combined. As one example of that power, it becomes possible to develop algorithms that specialize using techniques that are somewhat similar to C++ templates. Neil is going to talk a little bit about programming language features related to that concept. Yes.
Thank you. So type classes are a feature. There are a few languages that have type classes. Haskell comes to mind. The protocols that appear in a couple of different languages also very similar, not quite exactly the same thing, but very similar to type classes. And I'm going to talk about it in terms of a particular use case. So let's suppose you want to write a numeric algorithm, but you want to abstract it over the number type. You want it to work with doubles, you want it to work with ints, maybe you want it to work with complex numbers. You don't want to decide when you're writing the algorithm which number type you're going to use. But you would like to be able, when you call it, you would like it to be as efficient as if you had written it for the particular type that you're using it on. So here's a reduce function that adds up all of the elements in an array. It's abstracting over the number type. So it takes an array of some type t, it takes a 0 value, which is the initial value of your sum, and it takes an add function, which in C# parlance is a delegate. This would be a SAM interface type in Java. You'd probably pass a lambda expression when you call it. So the implementation is simple. We start out with an accumulator called result that equal to 0. We loop through the elements, and we use the add function to accumulate the elements into the result, and finally we return the result. And here we have a call. We call reduce. We pass the type parameter, which is int, which is the type of the value we want to use. We pass 0, and we pass the addition function. Now this works. The problem is, in practice, if you have a fairly large implementation with lots of functions in your numeric library, you're going to have to pass lots of little functions around your add and your multiply and your divide and so on. It becomes very awkward, and it's unlikely that they're going to be inlined. So your invocation of add, 3 levels down in your stack, is unlikely to simply be an int add operation when it gets to actual machine code. So the question is, can we do better than that? And if you have a language with value types and generics that, when instantiated on value types, are guaranteed to be specialized, you actually can do better than that. So I'll refactor this a little bit. I'll introduce an interface called monoid TC. Now, monoid is a mathematical structure that has a 0 operation, and it has an associative and commutative binary operation. So this monoid TC is an interface with 0 and add. Now the problem is, int doesn't implement this interface. So we have to somehow impose this interface externally when we're working with an int. And the way we do that, well, first, the way we use the monoid in the implementation of our reduce method now is we pass it as a type parameter. You can see this reduce method takes two type parameters, one T and one T monoid. But we restrict T monoid that has to implement the monoid TC interface. And we also say that it has to be a struct type, so it has to be a value type. So it will be specialized. Now, of course, it would be specialized even without that constraint if it's actually instantiated with a value type. I just put this here for clarity. Now, by convention, implementations of these interfaces should have no data. Now, of course, you want that to be enforced by the compiler somehow. What I'm showing you is the kind of thing that a language could translate a type class's language feature into. So this is the target of the translation. So it's a little bit awkward to do by hand, but you pass this type parameter T monoid, and it's not used as an argument, and it's not used as a return type. But the implementation creates a default value of that T monoid. And the default value is just as good as any other value because these monoids, they don't have any state. They only have functions. They have interface functions you think of as virtual functions. But so we call m.0 to get the initial value of our accumulator, and inside the loop we call m.add. We use the add operation on the T monoid. But because let's also look at where we use it. I created a struct int add monoid that implements the monoid for integers. It provides 0 as the implementation of the 0 function, and addition as the implementation of the add operation. And then when I finally call it at the end, I call sum. The sum method just calls reduce. But because it's passing a value type, int add monoid, as a type parameter, reduce is going to be specialized by the virtual machine so that at runtime we'll have a specialized implementation. M equals default T monoid disappears because there's nothing to do for that. The implementation of m.0, that's an interface call, but the runtime knows exactly what the implementation of that is. So the runtime can simply substitute it can inline the implementation and pass 0. Similarly, add, the runtime knows exactly what that is. It's the add operation on int add monoid. So it can inline that to a simple integer addition operation. So the result is that at runtime, this use of the reduce operation with the monoid can provide you with exactly the same machine code that you would get if you had written a specialized numeric algorithm by hand. I did that at the bottom just to show you the kind of code that you get. But you compile them both, you'll get approximately the same machine code and the same kind of efficiency. So the point is that value types and generics together are very useful as a target for other language features if you have guarantees that value types, that generics over value types are specialized. If you don't have that guarantee, it's a little bit more difficult.
As I said in the previous slides, generics are always logically specialized in .NET. There's no erasure that occurs in the .NET generics model, and both for reference types and for value types. But in practice, though, while the runtime must specialize the type system data structures for all of these types, the runtime does not actually generate specialized code for instantiations on reference types. In particular, the core CLR runtime specializes value types instantiation cogen, but not for reference types. Instead, for instantiation over reference types, we generate one copy of code that reaches into type system data structures dynamically to figure out exactly which instantiation value is needed for something like a cast or cast operation, yeah. In general, we find that specialization, it's really important to specialize for data layout, for local variables, heap data structures, that sort of thing. But for specialization, by avoiding specialization for reference types, we gain large benefits by reducing the amount of code that we have to JIT or interpret, and the sort of different variants of this code, saves space in the caches of the processor due to less code being in existence. But we get the benefits of, but when we work with value types, we get the benefits of specialization, because optimizations such as Neil described, or other things that you can do in a manner similar to C++ templates are very useful for great performance. Also, we've found that we've had these policies for many years around how specialization is done. And we find that our customers have developed dependencies on exactly the characteristics of our compilation model. We have a very important design principle, which is the idea of predictability of performance. And since we have that performance and customers have come to expect that a specific performance characteristic will happen forevermore, well, we have to maintain at least that level of performance. Code must appear to compile very quickly for reference types. If we added a model for specializing code for them, we'd have to make sure that it was all non-visible in the performance spectrum. And for value types, again, we have to specialize the codegen for them in the vast majority of cases, because otherwise our customers will find that the performance of their applications will drop unexpectedly. And so the choices we make, they have consequences that go on for quite some time, even if they're not semantically required. So how do we actually generate IL for generic code? The .NET IL is very similar to Java, but there's a few spots where it's a bit different. In general, a lot more of our opcodes actually take explicit type parameters. And nearly all of those opcodes can work with any type variable, with the general model of, if the type variable referred to as a value type, the opcode operates in the data of the value type. If the IL opcode refers to a reference type, the opcode operates on a reference to the object on the heap. There are some special cases, though, which are box, unbox, and constraint calls, which are used to make specialized calls. I'm going to start with the box opcode. So what we have here is a function, convert to object of t, taking a value of type t, and it simply returns as a boxed object, a boxed value type, the incoming parameter. This translates to the IL below, the load arg.1, load the first argument, box bang bang t, box using the method type variable t, and then ret to return the value. At this point, you can see that we have loaded arg1 onto the stack, and on the stack what we have is a type of type t and the value of 42. There's nothing on the GC heap. Move on to the next instruction. After executing the box, we'll now have as the stack, we'll have type object, and there'll be a pointer, well, or object reference really, to an object on the heap, which is a box int32 holding a 42 in it. How about this, though? Here we go with exactly the same IL code, exactly the same function, but the convert to object in this case is used with a string. We're passing test string in. And so we load arg1, load the first argument onto the evaluation stack, and we see it's still of type t, but now it's an object reference into the GC heap, pointing at a string object. Box is defined to not do anything for reference types. So here we execute the box instruction, and while we change type from t to object, what was actually present on the stack is not changed. It's still that object reference into the GC heap. I'm going to skip the next case talking about unbox because we're short on time. Here we are. To a little bit more complicated example, and this is a constrained call, which is a call to execute some a virtual call to manage pointer of some specific type. And this is used to implement the generic specialization behavior that Neil talked about. So here we have an interface I, which implements some function. We have a class C, which implements the interface. And of course, there's the implementation. We have some IL of use I of t, which simply will call the function as a generic type variable. And then to the right here, we have type, yes. I meant to do with this with a struct s. So imagine replacing class C on the right with struct s. So here we have an s, it's a struct passed onto the type passed, and we have a local, which was of type t, which actually has the value with the struct within it. After executing the loadarg address function, so this generates a managed pointer, and that managed pointer points at the local. We can then execute the callvert instruction, the constrained callvert instruction, and that will directly call the function on class or struct s, and we'll place a 3 onto the stack. Major difference here is from what we have here. Here we have a class C. So this is the class case. When we execute the first instruction, we still generate a managed pointer to the variable of type t, but it's actually generating a managed pointer to the local. And so we now have 2 pointers going on here. The evaluation stack has a pointer to the local t, and the local t has an object reference that points into the GC heap. The constrained call opcode will then double dereference and perform an interface dispatch to call the function. And of course, you'll still get a 3 because the implementation of all of these is all the same, just the difference between being a structure and a class. So what are the challenges we see with generics and value types? They work really well as a developer model, and it's very easy to sit down and write C++ templated style code or to get really good performance. But when you do that, there are very high levels of code expansion. We generate many different copies of very similar code. And that's the thing I talked about a little bit earlier, where we use up space in the caches if you execute a lot of this. In .NET, generic IL is pretty inefficient to interpret. Any given method reference in the IL may refer to many different things depending on what instantiation is in use. This slows down both our JIT and makes it quite difficult to cache results. With reified generics comes more data structures. We have to have multiple copies of statics. We have multiple copies of type system data structures. We have to find the right place to put all of these. What lifetimes are these associated with? These are all fairly difficult questions to answer. And even when we don't generate multiple copies of code, we have code that is shared across multiple instantiations. So it needs to reach into type system data structures to get whatever the right answer is. I think we're actually at 45 minutes, so I think I'll just break straight to, we can use value types and generics for many purposes. They're very useful. There is some real significant interactions between the two. In .NET, when we use the value types and generics together, or really just value types or just generics, there are a collection of performance guarantees about how exactly the code is expected to execute. For some examples of how to use value types and generics to get really good performance, I'm pointing you at a blog post one of our performance architects put together, talking about some specific improvements made in .NET Core 3. These are an example of the sorts of improvements you can get with value types and generics and the combinations of the two. Questions?